Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
I'll just share my screen.
Sendil sir, am I audible, sir?
Yes, sir. Yes, sir. Please, Dr. Kumar, can proceed.
Yes, sir. So it is my privilege to introduce our today's session chief guest, special speaker, Dr. Siva Shanmugam, sir. He is from our well-known institution, National Institute of Technology, Trichy. He joined as associate professor in the Mechanical Engineering Department from 2018. Also, he completed his UG in Mechanical Engineering from Bharatdasan University and completed his PG from Anna University. He completed his doctoral degree from the field of finite element simulation pertaining to laser beam welding process in NIT Trichy in 2012. His research targets were wire arc additive manufacturing, finite element simulations of welding process, fatigue and fracture. He has authored more than 135 papers in international and national journals and conference proceedings, and has attended conferences from various countries like Czechoslovakia, Swiss Republic, Austria, France, Singapore, and Thailand. Also, he is a reviewer of various journals like International Journal of Advanced Manufacturing Technology from Springer, Journal of Experimental Techniques from Wiley Publishers, Journal of Materials and Design from Elsewhere, Journal of Mechanical Engineering Science Part C from Sage Publishers, Science and Technology in Welding and Joining from Taylor and Francis, also from Material Letters from Elsewhere. He has completed several sponsored projects worth about more than 1.3 crore, funded by various funding agencies like BHEL Trichy, NLC, DST, and VSCC ISRO. Currently, he is working in a sponsored project worth about more than 18.5 lakhs under the TAR scheme of SERB DST. He is also in innovative teaching methods followed his teaching. His teaching interest on the other hand includes strength of materials, finite element analysis, engineering graphics, welding technology, and non-destructive testings, also in product designs. With his vast experience in these fields, we'll go for today's session. I hand over the sessions to Dr. Siva Shanmugam, sir. Sir. Hello, sir.
Siva, sir. I think he is not in. Let me check out.
Actually, he lost his connectivity.
Yeah.
His app got crashed. He said now he will join within a minute.
Okay. In the meanwhile, I request Mr. Kalyan to post the feedback link for the first session. For every session, the link will be posted.
Feedback form posted.
Okay, thank you.
This feedback form will be valid for 1 hour only. So I request the participant to fill the feedback immediately. So within a couple of minutes, the second session will start. Thank you.
Prabhahar, my screen is visible?
Yes, visible.
My presentation is visible now?
No, your screen is too much zooming.
Now it is there? Now my screen is visible or?
No, only that message you are sharing your entire screen. I think zoom is very high, I think so.
Now my screen is visible.
Yes, 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 yes. Clear, clear. It's clear.
Now my screen is visible.
Yes, yes. Visible, visible.
Okay, okay. Sorry, I missed out the introduction session. I don't know how you are introduced me. No problem at all. Shall I start the proceedings, Prabhahar?
Yes, 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 yes.
Okay, okay, okay. Thank you, thank you. Very good evening, friends. We are approaching the night. It's very difficult to open your eyes because you have full hectic scheduled in the morning. You have attended all the classes. You took the classes. You have handled the classes. It's very difficult to open your eyes. Anyway, I try my level best to open your eyes. Please, my dear friends, if you have any work related to this, some other things of household things and all, please pay your attention for another 45 minutes. I am not going to drag my presentation. Please open your eyes for 45 minutes. It is not only mere sharing the information available in the systems or in the open literature. It is the information that I'm going to share my personal experience had with the 3D printing technology or with the additive manufacturing technology. And before enter into my today's topic, I want to thank my friend, my close friend, Professor Prabhahar, who have organized this wonderful workshop and ATAL program, and he provided me an opportunity to be a part of this wonderful program. And the topic assigned to me is something like a comparative analysis of three-dimensional printing techniques for engineering applications. I am not going to move my slide for another 5 or 6 minutes. A preamble about this topic is highly essential and it is relevant to the topic what is intended today for the presentation. See, when you go for a 3D printing, everywhere it is something like a talk of the town. All the people, for example, if I put a request, you have a 3D printer available in that institute. Yes, I have a 3D printer. It is something with respect to the fused deposition modeling. We are printing something about the models. We are printing something about the vegetables. So many things are there. We are printing our own product and all. But I have some basic doubt with respect to the 3D printing and additive manufacturing. So when I had a doubt, normally as a faculty member, we are going for a Google search and we are going for in-depth search of the information. What is the difference between the 3D printing and additive manufacturing? And my second question, my question I had in my mind is something like, why, sir, we are going for additive manufacturing? Because we have a different technology. We have a comparative study that I'm going to discuss in the next slide. I have something with basic doubt when I'm preparing this presentation, not for today's presentation. When I prepared the presentation for addressing to my undergraduate students, I had some sort of issue. What is that? Because I want to inculcate, I want to share that experience, I want to catch them in depth. Because when we speak something about the fundamentals, we must be very strong in our fundamentals, then only I can catch the audience. It may be an undergraduate or a postgraduate or a postdoctoral fellow or something like doing a PhD work on 3D printing or additive manufacturing. When I'm going in depth, I could understand that 3D printing, additive manufacturing is the part of the 3D printing, but 3D printing, normally the word emerges with respect to the industrial scenario is something to get the realistic shape of the product. Sir, I have a product, I have a design in my mind. I want to find out what is the capability of the product in a real sense. I want to visualize something, the idea or the model that I have generated in the CAD software. Either it may be a CATIA or something like Autodesk, or it may be a Fusion 360, or it may be a Solid Edge or SolidWorks, etc., etc. So the 3D printing seems to be the conversion of the model, three-dimensional model to a product. Product means you can visualize. You are not supposed to put that product for the real application or the real. It will not use as an end product. You can see the design may be converted to a product. That is something called 3D printing. So if you have any doubt, you just go in depth and do a literature survey or search information. You will get this information what I have delivered now. 3D printing, I just repeat once again, 3D printing is something like conversion of a three-dimensional model into a product that should not be fulfilled by the customer, that will not be utilized by the customer. You are going to visualize about the product that you have designed. When you go for this additive manufacturing means I am talking something either by means of a powder technology or by means of a wire technology that I am going to discuss in the forthcoming slides. My humble request once again I put forward through this forum, please make it your presentation, make your vision somewhat wider, and your ears should be widened in such a way that to grasp some information with respect to the 3D printing and additive manufacturing. It is not only a part of the literature, it is the experience that we have gathered at NIT Trichy. See, that is something like a 3D printing. When you go for an additive manufacturing, see, the three-dimensional model is converted to a real product. This real product will be utilized by the customer. Very important. You are giving the product, you are feeding the product to the customer directly. It is not only give the real shape, it is intended for the purposes, for the application, for what purpose you are developing, that should be fulfilled by using the technology of additive manufacturing. See, sir, why, sir, it is a talk of the town? Only in 5 to 10 years they are talking about additive manufacturing, or maybe around 14 or 15 years. Sir, what is the real capability of the additive manufacturing? Before that, I want to give something with respect to that, a conventional manufacturing method or conventional way of developing the product. See, when you go something around 40 years back, if I have a time machine, so I am just rotating the time machine, you are going something around 1980s or 1990, where we have our first industrial revolutions, or a second mid of that second revolutions. We have electrical power, we have a machine tools, we are using all our conventional data. Conventional means what we have? Sir, we are getting a requirement from the market survey. Yeah, administration people, that is an MBA graduate, can gather the information from the market. So based on the market survey, idea is generated. Once the idea is generated, the purpose of the design engineer to convert the idea into a proper design, and it will be made by the draftsman. Clear? A diploma engineer is debuted for that purpose, and he converted the real-time data into a 2D drawing. So once the 2D drawing is created and it is endorsed by the design engineer, it is giving into the shop floor. It is provided, it is submitted to the shop floor, where the shop floor manager will get into that and he will give the guidance. He will provide the guidance to the employee who is working on the machine tool, a proper technician. After interpreting, after getting into the design, after available in the 2D drawing sheet, he can design, he can plan the schedule. What about the material? What about the tools that I want to use it for creating this product or the component? But the problem arises. When the problem arises, if the design is something like an odd. What do you mean by the odd design? Sir, instead of a 10 mm drill bit, the design engineer made 11 mm drill bit, 11 mm drill hole. So the drill bit pertaining to 11 mm is insufficient, is unavailable in the shop floor. So then he will report, sir, 11 mm drill bit is unavailable, is not available in the shop floor. Then he put that information once again to the production manager. Production manager took the information from the technician and he shared that information to the design engineer. So the design engineer once again will rework and he will modify according to the machine tool available in the shop floor, and once again it is fed to the draftsman. A draftsman will do the rework and he can do the modified design, and once again it is going to the production manager, end to the technician, and he or she can develop the product. See, what is the problem associated with that? The time. So it will take minimum 6 months to 1 year to get the realistic shape of the product. Then only you can deliver it to the customer. So what happened? The competitor will reach the market. Before that time, subsequently competitor will do some sort of thing and the competitor will reach the market within the stipulated time. To avoid this problem, they have introduced the principle called concurrent engineering. What is the concurrent engineering? Something in the year of 2000 or 1998 to 2004, concurrent engineering plays a predominant role in the market. What do you mean by the concurrent engineering? It is concurrently discussed by among the people of the organization, and they will sort out the issue as and when required. See, there is a representation from the production manager team, there is a representation from the technical team, there is a representation from the administration, there is a representation from the finance, there is a representation from the design team. So they will solve the problem. If there is a 11 drill, so the production manager at that time he can question, no, 11 is very difficult to do it in available materials available in the shop floor. Then instead of 11, the design engineer may look into that and he can correct, he can do the modification as and when required. So concurrently, they sit together, they do the brainstorming section, they'll solve the problem and they can give the design to the do the production manager. Production manager can deliver the design to the technician. Technician will completely define, will completely complete the product within the stipulated time. But what is the problem associated with concurrent engineering? So many people are involved together and they are finding out the solution of the problem. So previously a conventional issue. Second one is the concurrent. So many people are involved. See, now there is a modification. There is an advancement from concurrent engineering to the additive manufacturing. Sir, side by side, we have another 2 manufacturing methods that I am going to discuss. What is the additive manufacturing? What is the need of industrial 4.0? And we are prolonging to that industry 5.0. What is the 4.0? See, in that you are going for a 3D printing, additive manufacturing, etc., where a single person is sufficient to do the design. Once the idea is available, once the idea is provided to the design engineer, single person is sufficient to do the design and to make the component with the single machine. That is the beauty of development from concurrent engineering principle to the additive manufacturing. Sir, my second question, why additive manufacturing? Very important question. Sir, why is there additive manufacturing? Why not we have some other methods are there? Why everybody is talking about the additive manufacturing now? See, the main idea behind that, you are doing the design without following any rules and regulation. Without rules and regulation means it is putting an underline over here. Without maintaining any standard, you can make your design and the design may be converted to a real product. That is the beauty of additive manufacturing. It is something called freedom of design. If you take additive manufacturing, if you put a ChatGPT or something like an AI, refers something like a freedom of design. Whatever may be the design that you have in your mind, that you can convert to a realistic shape. That is the beauty of additive manufacturing. This is something with respect to the preamble. If somebody raises that question, why? What is the need of additive manufacturing? It is something called freedom of design. The design will be converted by a single person to get the realistic shape of the component. See, and what about the agenda of today's presentation? So we have a comparative study. So that is why I have provided so many preamble with respect to that additive manufacturing. What is the difference between 3D printing and additive manufacturing? What is meant by the conventional methods? What about the concurrent engineering? Everything that we have discussed to create a basement. So once the basement is pakka, you can create a bungalow or you can create a kucha house, mud house, hay house, whatever the thing you want, you can build it. So I am going to touch most of the information available here. Comparative study. What do you mean by the comparative study that I am showing in the next slide? And I have the general benefits of this additive manufacturing. And I'm going to define the additive manufacturing by means of ASTM. Standards are highly essential. When you want to make a product, you have to fulfill the standard. Then only universally the people will accept and they can use your product for their application. And the fourth one is the buy to fly ratio, a very important terminology that I'm going to discuss in today's forum. And we have the classification, as my work is intended towards the classification of additive manufacturing. What do you mean by the process flow? How the process starts and how it is going to end? And what about the different applications available? Where are the areas I can put my nose? I can put my additive manufacturing to fulfill the requirement of the people. And advantages, capabilities, and also what NIT Trichy is working on that. See, we have a comparative study. A very important, if you want, you can take a screenshot of this information because you have a mobile, you can see it from the mobile or from the iPad or from the electronic gadgets. You take the screenshot, very important slide with respect to the comparative study. Every time there is no need of going for additive manufacturing. Very important thing. Please make a note of it, friends. No need of every time you can go for additive manufacturing based on the requirement. Sir, I want to produce a single component n number of times. Then additive technology, additive manufacturing technology is not providing the good solution. In such cases, you have to go for the formative. Formative means it's something like a casting process. You can go for a high volume. Materials is deformed to a desired shape using a combination of stress forces and melting. For example, injection molding involves forcing a molten plastic into a catty that sets to a desired shape upon cooling. Sir, every time don't go for additive. Based on the requirement, you can select the methods. First one is the formative technology, something like a high volume. The mass production of the component, of single component of similar type, may be something in thousands or in terms of the lakhs. When you go for a subtractive, sir, I want a high precise component. My component should speak. There should be some sort of tolerance, some sort of fits, some sort of warpage or some sort of shrinkage. In such cases, you need a high precise component. In such cases, we have a technology called subtractive manufacturing technology that we are using a 5-axis VMC, vertical milling machines, or a lathe machines to machine the component. We have so many varieties of machine tools available nowadays to get the subtractive manufacturing technology that will provide a high precise component. 3D objects are fabricated by removing material from a starting block of a material. Sophisticated CNC machines are available in that world with a less cost, enable the precise control of a range of cutting tools to achieve a very precise tolerances. So you can very stringent to the tolerance. In such cases, don't go for additive manufacturing, go for the subtractive manufacturing methodology. And the last one, sir, I want to convert my own design, sir. I have my own, I didn't follow any sort of standards, any sort of tolerances fixed. I want to get the realistic shape of the component. Then go for that additive. It is something like a freedom of design. In the word also they have mentioned is high freedom, high flexibility in your design. A transformative approach, a beautiful word. English is a beautiful word where you can convey all this information as a nutshell. So a transformative approach that removes the constraint of a formative and subtractive techniques. Almost any geometry can be fabricated. If you can conceptualize it, it can probably be realized. A beautiful word. If you have a concept, if you have an idea, that may be converted as a real shape, a real you can take it and you can enjoy what is this is the design that I have made. So I have intricate areas, I have some sort of aesthetic appearance, I am giving a new look to the component. That and all you can visualize using this additive manufacturing. My dear friends, my humble request is don't select additive manufacturing for all the cases. Not for the most of the cases you can select, but not for all the cases. See, when you go for a high volume production, please prefer formative. If you want a high precise component, you go for a subtractive manufacturing methodology. And third one, if you go for a high freedom of design, then you can print the product or you can do the product additively by layer upon layer manufacturing. And this is something about a big tree, a banyan tree with all the branches. I have provided all the informations available with respect to that rapid prototyping technologies. I have classified under 3 different headings what we have. We have a powder, we have a liquid, and we have a solid form. Powder, we have a beautiful terminologies are available. By a component and a binder, we have only one component, that's no binder here. For the first cases, component. In the second case, we have a 3-dimensional printing where we have the binders. Under the component, we have a selective laser sintering. So most of the plastics, you are not melting the material, you are going very close to the melting point of the material. Selective laser melting, you are melting the material. And electron beam melting, with the help of high energy electrons, you are melting the powder materials. And direct metal laser sintering. So there is not much differences between selector laser sintering and direct metal laser sintering. Sir, what is the difference here? We are going for a metal, that is we can go for that plastics, polymer type of a material. And when you go for a component and binder, it is something called a 3-dimensional printing. When you have a resin, something like a liquid arrangement, we have a inkjet, multi-jet modeling. It is something called that MJM, and the droplet on demand inkjet, that normally what you are using in the inkjet printer. that we can use the principle of layer upon layer. It is coming under the category of liquid. Liquid is that raw material or the feedstock. And when we have a photopolymerization, it is coming under the two different category. We have ultraviolet. With the help of the ultraviolet, you are melting the material. That is something called the polyjet. And we have a laser, that is something called the stereolithography. It is a well-known practical thing. Most of our engineers are working in the area of SLA. That is something about stereolithography. Coming to the solid, we have a glue. We have a gluing sheets and we have something like an extrusion. When you go for a laminated sheet, something like that, gluing sheets, we have the so-called laminate object manufacturing, and when we have an extrusion, it is something called that fused deposition molding. If we take the FDM, most of our institute, we have in each and every lab of mechanical engineering, they have this FDM, they have the printer head, they are feeding all the wires and they can print according to the requirement, according to the design they have developed. This is with respect to that broad classifications. I have one more classification that I am going to discuss in the forthcoming slides. Sir, yes, sir. The next slide will speak about the real thing. I am not going to do that visualization. I am going to deliver as an end product. What about the classification of main additive manufacturing? Sir, that is something like a rude, like a banyan, big. Now I make it as somewhat crisp and short classification of main additive manufacturing. So I am categorizing this into two different categories. Please, my dear friends, please, it is very important thing. I am really enjoying for giving me an opportunity to handle this session irrespective of the time. Even if you ask me to make it at 12 o'clock, the same Josh will come because it is very important. You are going to play with the product, not with producing a paper, especially in that additive manufacturing journal with having an impact of 15 or 20 or Springer Nature is something like a 25. No. It is you can do your own job and you can do an enormous amount of the consultancy work. Only thing is, what is the method you have followed? Sir, this is an opportunity for you to make a wonderful sort of things. You can take it as a hint. Anytime you can approach us or approach to anybody who are working in this area where you can make your wonders with the help of this mission too. And when you go for these classifications, we have a beam technology and we have arc technology. That now I am directly getting into the point what I mean here. So beam, under the beam, we have a two different classification. We have a laser and we have an electron beam. Laser is used for melting the powder. Here, electron beam is used for melting the powder. Under laser, we have a two different feedstock. Laser electron beam is coming under the heat sources where you are getting out the heat. The heat energy is getting out from the light. Heat energy is getting out from the high energy electrons. And what about the feedstock? Sir, either you can feed the filler wire, this filler wire of different material, maybe of aluminium, maybe something like a cobalt alloy, maybe a nickel alloy, Inconel 617 or 625 or 618 or Inconel 71, whatever may be the filler wire, that you can feed it, and this incoming laser is used for melting the wire. And the same thing, instead of wire, you can put the powder. Powder will be melted by the incoming laser beam. Coming to that powder, we have another two different technology. First one is the bed technology and another one is the blown technology. Bed technology, I am going to play a beautiful video where you can get the gist of that information, what I mean here. Powder technology, there is something like a nano level powders are there, micron level powders are there. Based on the product that you want to make, want to manufacture, you can select the size of the powder. Bed technology, the bed means you are keeping the powder, you are placing the powder on the Z table. So you are putting the laser beam. The laser beam is used for melting the powder. Wherever you are keeping the product, that area alone will be melted. Remaining area, you can use it as you can recycle it and you can put once again the powders on the table. And that Z table will move along the negative direction. Please, layer by layer means, so it will move along the Z direction. Material will be built along the positive Z direction. I repeat once again, Z is representing the table Z is equal to 0. So first when you start the laser, it will melt one layer. So material will build in the positive Z direction, and movement of the table will happen in the negative direction of the Z table. Negative Z minus, building of material is on Z plus. That is something called the bed. What happened to the blown technology? Blown technology is another very beautiful thing where we have the coaxial nozzle. The incoming laser, the laser will come from the nozzle. So in the nozzle itself is designed and developed in such a way that the center you are getting that laser, circumference to that laser you have a passage, you have an orifice in which powder will be fed into the table. So both the focal length, that is that powder which is coming out from the coaxial nozzle and the laser will be merged together at the focal point. So this incoming laser will melt the powder and you are getting the deposit on the Z table. That is something called the blown technology, that is called the bed technology. So in bed technology, you are going to pre-place the powder, but when you go for a blown technology where you have a coaxial nozzle, at the circumference of the laser, you are getting out the powder, center you are getting out the laser. These two focal lengths are matched together to get the melt of the material. So if you are using the bed type of a technology, we call it as a selective laser melting. Selective laser melting. And when you go for a blown technology, it is called direct laser fabrication. Sir, when you go for a wire arc, what is it? When you go for a wire, laser with wire, laser arc additive manufacturing or laser hybrid wire arc additive manufacturing. These are all the terminologies normally used by the expert in the industrial scenario. I repeat, when they are using the wire and with the laser arc additive manufacturing or laser hybrid additive manufacturing, they can use this terminology. And when you go for an electron beam, we have a wire, same thing, you can fit the wire and the side direction. That process is called CIACI. That process is called CIACI. If you want to get more information with the CIACI, you put in the open sources, you will get so many information with respect to the CIACI. CIACI means the where you are feeding the wire to get the from the fast moving electrons are used for melting the wire. That process is called is said to be a CIACI. And when we have a border type, same thing as I mentioned in that bed type, like Z is a minus negative minus Z and positive Z. Same thing, electron beam also may be utilized for making out this technology. Powder, we have a bed and something called that electron beam melting. EBW, electron beam welding, where W has been replaced by M, electron beam melting. This and all is of precise control, where the powders are used in terms of nanometers or in terms of the micrometer. You can precisely control because the lasers are you can operate in terms of micron level. And we have a separate technology, called the arc technology, where our conventional welding machines have been utilized for creating the additive manufacturing component. Arc as the power source, the heat source, where you can get the arc, especially by means of a conventional welding. Conventional welding means what are the conventional welding we have? We have a tungsten inert gas welding, we have a metal inert gas welding, we have a plasma arc welding. So these conventional arc welding processes are used for melting the filler wire. The resulting process is said to be wire arc additive manufacturing. If we go for a large scale of heavy component, this is the only process available in the world where you can make wonders. I am going to showcase all the information with respect to the wire arc additive manufacturing. Why I am gathered this information, why I am sharing this information, why I am taking the privilege of praising that wire arc additive manufacturing, because you want to meet the applications of the real world scenario with least expensive. It is an inexpensive process, but when you go for a laser or electron beam, it is so expensive to fulfill the requirement of the current scenario. Now, I am going to play a beautiful information with respect to the two informations what I have shared. When I'm talking something about the general benefits, reducing the time to create a prototype of a product and itself from the month to weeks and days. As I mentioned here, for that only I have provided a preamble. Before getting into the real presentation, I have provided a preamble with respect to the conventional manufacturing method and then the concurrent engineering to give an eye opener, to provide an information with respect to the time to market within a stipulated time. within days, within week, you can reach your product to the market. You can fulfill the requirement of the customer within a week. A real tangible model of a future product is easier to design and present to the customer. A very beautiful sentence. See, a real tangible. So you have a manufacturing method available. So whatever may be the design you have, that you can readily provide it to the customer. The physical model is easy to correct. Errors are possible in the graphical representation of the product. Sir, you can, when you do a modeling itself, you can find out, oh, these are all the errors that will come. Oh, you have to do the repatching or the patching of that work, and you have to remove the bugs, errors with respect to the product. That is possible, that is feasible only with the additive manufacturing. Decrease in the cost of the tooling, because you are going to use one machine where you are going to do the design and where you are going to manufacture. Decrease in the cost of the tooling and the cost of design iterations. And the last point, the cost of product prototypes is lower than that of the traditional methods, because you are going to provide only one product. There is no need of high precise, there is no need of high volume. As I mentioned in the comparative study of formative, subtractive, here I want to deliver it to the customer to attain the attention of the customer. I am going to deliver it to the customer. These are something with respect to the general benefits of additive manufacturing. Very important, friends, as a crisp, as my friend Joseph Davidson provided, what is the difference between industry 4.0 and 5.0? That is a nutshell. So that is very important to provide as a concluding marks. Here, what I have discussed so far, I have made it as an inferences, because very important, I want to make some sort of inferences at each and every junction. Otherwise, you will miss out my presentations, what I mean here, what I am presenting here. So our attention is highly important, where I can provide, I can feed you appropriately. So what we can gather, benefits of sound additive manufacturing strategy. Any method you can adapt. What are the things I have discussed with the RP technologies and classification of main additive manufacturing? I have an optimized product design. I have mitigate supply chain risk, because there is only a minimum component. I can fulfill the customer need as and when required. Reduced cost, reduced inventory. There is no need, because I can easily reach the market. I am not keeping it for 100 goods in a time. As and when required, I am going to deliver it. No, within a day I can fabricate, I can deliver it. There's no need of keeping as an inventory. Reduced inventory, speed up new product development. Any product emerged in the market that you can develop by means of this additive manufacturing technology. Increase operational efficiencies. Efficiently, you can use the system and you can use the process flow. So this is something with respect to the benefits of the sound additive manufacturing. Now, I am not going to take all the things separately and I'm going to give the advantages, disadvantages, applications. No, I am going to compare between the powder and the arc. Powder means what? You can use the laser or electron beam. Arc means where you can use the TIG or the MIG or the plasma arc source, and you are going to compare which one is playing a predominant role in the market. For which applications, what process can be suited, that you can list it. That I am going to list it over here according to your requirement. According to the requirement, you can use the process. Okay, so coming to the part of definition, very important, because when you talk something about the phenomenon, when you talk something about the fundamentals, you have to define it properly. What is the definition that I'm going to provide here? ASTM, American Society for Testing and Materials, they have defined additive manufacturing a process of joining materials to make objects from three-dimensional model data, usually layer upon layer, as opposed to subtractive manufacturing methodology. A beautiful word. So from the definition itself, it is a self-explanatory definition. There's no need of interrogation, something available in the interpretation of the definition, not at all required. See, it is totally opposite to the subtractive manufacturing. But if you ask me whether subtractive manufacturing methodology is required, yes, sir, 100% is required. Sir, when it is required, sir, I am going to discuss in the forthcoming slides. Don't worry about that. Sir, additive manufacturing is a technology that promises to reduce part cost by reducing material wastage. Sir, I didn't touch that material wastage. I didn't provide any sort of preamble or a small introduction with respect to the material wastage. I have discussed more about the time to market, a reduced time to the market. That is that. First advantages is something like that, reducing material wastage. The second important advantages of AM is something like a time to market. You can easily reach to the market within the stimulated time. That also I'm going to give it in the case study. In the van, sir, what I'm going to take? I'm going to take a wire arc additive manufacturing because it is a strong area. Because I'm giving a generalized information, you can read it from the generalized book and all. But when you give something like a very pinpointing with respect to one technology, and I'm going to compare with other technology, that should be more beneficial. That should be something like a honey flavored medicine. I want to take the medicine. For that, what you can dip the medicine inside the honey and swallow it. That's all. Or we have tested the honey, and also automatically medicine is injected to the blood. So that is it serves the two purpose. Similarly, I'm going to take the arc additive manufacturing and I'm going to compare with the powder technology. Wherever you want, you take that additive wire arc additive manufacturing. Wherever you want to take the powder technology, you can take that powder technology. It is up to you. It's up to the decision. It's up to that requirement of the industry or requirement of the product development. In the wire arc additive manufacturing, three-dimensional metallic components are built by deposits, beads of weld metal in a layer by layer. A very simple thing, sir. I have a welding touch where I can use the filler wire. It is a MIG welding process. I am going to deposit a single bead. Above, I am going to deposit another bead. I am going to deposit another bead like that according to the requirement of the component. According to the shape of the component, I am going to deposit the weld beads. Sir, what about that, what about that stickiness? What about the layer stickiness between the two layers, between the subsequent layers? Sir, we have a very good bonding strength because we are playing the material and we are affecting the material metallurgically. If you are affecting the material metallurgically, then you can achieve a very good bonding strength. And finally, wire arc additive layer manufacturing can be used to deposit a variety of materials. There is no limitation, sir. So if we can develop a filler wire, tomorrow I can use my robo welding machine. I can feed your filler wire. I can deposit the filler wire on the substrate material. So that is why I have mentioned here is only of steel, nickel alloys, titanium alloys, sir, aluminum alloys. We can have a stainless steel alloy. You can take a cobalt alloy. Any material, if it is in the filler form, I can develop, I can make it as an additive manufacturing. I can create a component through additive manufacturing route. So there is a photograph provided over here. What is the photograph? Sir, I have provided one photograph above in that layers, different layers of beads are deposited one above the other. See, there is a plate available at the bottom. That is something called the substrate. So what is the purpose of that substrate? Substrate is the one. See, when you go for an hostel, I am staying in the hostel, or otherwise I am taking my dinner. So what is it normally I'm going to take? Sir, I prefer to take the chapati. What is I'm going to do? I am going to take a plate. Above that, I am going to keep one chapati. I am going to put a dal, or I am going to put a sabji, or I am going to put something like a gurma. After that, above that, I am going to keep another chapati, gurma, something like that. So I need a plate to carry this material, to carry this chapati, to carry this chawal, to carry the rice, to carry the sambar, to carry the sadam. Above that, I'm going to put something like a rasam, or I'm going to put a parupu. I'm going to mix it, I'm going to take it. Correct? Similarly, here you need a substrate. Substrate is inevitable. You need a substrate. Above that, you are going to put the layers of bead, one above the other. See, it is provided in a different orientation. See, that is the only process available in that fold. I am challenging you, my dear friends. Without support structure, you can create this inclination. Either you can go for a 65 degree or 63.2 degree or a 64.2 degree. That is the only process available in that world is orienting the torch, welding torch, and you can lay the number of beads one above the other. See, the first bead is something very close to that 65 degree. Second bead is very close to that 75 degree. And the third bead, third wall is very close to that 90 degrees. So like that, you can make the orientations according to the requirement. So if I want to make I want to make some sort of stiffener to the existing plate, existing component. I want to create a stiffness with a different angle. You can use that existing component as a substrate. Above that, you can lay the number of filled bits one above the other to get the or to fulfill the requirement of the stiffener. And what about, sir, we can go? What are the real things that is required? This technology adapts arc welding tool. Arc welding tools means what? TIG, MIG or plasma, and filler wire as a feedstock for additive manufacturing purpose. Sir, it is a new. No, sir, it is not new, sir. It is 105 years old, sir. See, the first patent was filed in the year of 1920, filled and filed in the year of 1920 by Baker. Modern welding and automation technologies provide opportunity that were not previously available. They have introduced the concept of 1920. After that, the Cranfield University of UK, you please, if I find any time, you can Google it, what they are doing at Cranfield University. Cranfield University, I can claim that they are the father of this thing. They are doing a wonderful job. They are working across the world and they are delivering the component across the world with the different varieties of combinations, functionally graded materials. Anytime, if time permits, you just Google it. Wire arc additive manufacturing by Cranfield University. You will get so many information. It will be enriched your knowledge with respect to that additive manufacturing. Sir, what my claim? High deposition rate. You have a very huge deposition because you can move the welding torch in terms of meters, 2 meters per minute. The latest what we have is something like a 3 meters per minute. The OTC Daikin people climbing that we can move the torch around 3 meters. You see something like a 3.25 feet into 3. Something very close to 10 feet you can move the torch within a minute to deposit the materials. Sir, a high deposition rate, low material and equipment cost, because a robo something you can get it for 15 lakh rupees, a weld power source maybe something around 10 lakh rupees, and you have a work table, accessories, a shielding medium, etc., etc. Within 30 lakh rupees, you can make wonders in the laboratory. And good structural integrity. As I mentioned over here, you have achieved a good metallurgical bonding strength. So makes that process more, not a difficult one, maybe a very feasible and very easy process. Wire plus arc additive manufacturing, a suitable candidate for replacing the current method of manufacturing. Maybe something like a solid billets, machining, and large forgings, especially with regards to low and medium complexity. Sir, I have a small miniature component. Then you are not supposed to use that wire arc. In such cases, we have another classification of powder technology where you can use the powder technology to print a small component. Here it is only for the low and the medium complexity parts. So why, sir, already they have made a research? No, sir, still it is required. So many things we can do. We can change the process parameter. We can change the building direction. We can do the material deposition strategy. So many things are still growing on. There is a pressing need for the development of the process that could replace the current method of manufacturing large structures such as cruciform, stiffened funnels, wing ribs. The entire aeroplane wings can be developed using this technology, which are machined from the billets or the large forgings, where I'm going to introduce the concept of buy-to-fly ratio, the unsustainable buy-to-fly ratio. Please, friends, please, I'm going to take another 1 minute. It is a very important terminology. You can put this question against any student. What do you mean by the buy-to-fly ratio? Yeah, very important ratio. It is a ratio between the mass initial and the mass final. Sir, when you go for a subtractive method, sir, I want to create this blade, sir. This blade is made up of a titanium material. The end product, for example, the size of the end product, for it is something an odd one. So, for example, I can take a small rectangular block. Sir, the end product, what is that we have? Sir, it is something like a 1 feet length, 1/2 feet, that is something like a 0.5 feet width and thickness of 10 mm. Sir, for getting out this product, you have to provide a block more than that of this size, correct? When you go for a conventional subtractive manufacturing. When you go for a subtractive manufacturing, what is that? Sir, length, it is 1 feet. Sir, I want to procure a 1.5 feet length. 0.5 is the width. Sir, I can go for a 0.75 feet width or a 1 feet width. Thickness is 20 mm. I can go for a 40 mm. So, 40 mm. Sir, what is that? 1.5 feet cross 1 feet into 40 mm, what is that density? What is that weight of the component? For example, weight of the block is something around 5 kg. When you machine it, it will be reduced to 1 feet length, 0.5 feet width, and thickness of 20 mm. So it is reduced to half along the thickness direction. So the weight is reduced to from 5 kg, the final product weight is something around a 2 kg or a 2.5 kg. Now you consider 2.5 kg. Then how to calculate this by to fly ratio? Mass initial is something like a 5 kilogram divided by 2.5 kilogram. What is the ratio? It is something like a 2:1 ratio. So this is for a simple case. When you go for a big something like a this type of a model, this type of a thing, you can go for that original block weight is something like a 20 kg. Final product weight is only of 2 kg. In such cases, 20 kg divided by 2 kg. End product is only 2 kg. For that, you have selected a 20 kg. 20 divided by 2, it is something like a 10:1 ratio. Sir, 18 kg of material have been wasted. 18 kgs of material have been wasted. So that is why in go for a gold shop, they will put add-on. That is the wastage charges. Wastage charges are added to the product cost. Clear? When you go for a conventional manufacturing methodology, because you are reducing the size of the component to get the high precise component. From 20 kg to 2 kg, 18 kg of material is added on to the product cost. 1 kg of titanium nowadays, it's very close to 13 to 15,000 rupees. Maybe something about a titanium 6Al4V. If you take a 64, Ti64, 64, normally they call it as it is a biocompatible material, is especially used in the aerospace industry, predominantly used in that aerospace industry. You see that 18 kg into 15,000 rupees, that wastage of material is added to the product cost. That is why you are having a very high buy to fly ratio. But when you go for a near net shaping using the additive manufacturing, you can procure the kg, the final mass, the final weight of the product is only 1 kg, then you can procure a 1.5 kg filler wire. That is sufficient. Only 0.5 kg is going as a wastage. So now you can see 1.5 kg of filler wire is reduced to 1 kg of the product. Sir, 0.5 is used for machining, for peripheral machining to get the finish of the component. 1.5 kg is reduced to 1. Only 0.5 kg is wasted. The buy to fly ratio is something around 1.5:1. Sir, mass of initial 1.5 is reduced to 1. This 0.5 is going as a wastage. So that is why I have claimed that even you are working with additive manufacturing, subtractive manufacturing is highly essential. Sir, can you provide some small example? Yes, sir, I am going to give a small example. In my first slide, you see that before machining, after machining, I have made some sort of small photograph. Before machining, you are getting some sort of undulation. After doing the conventional machining, my weight is reduced. For example, this is 1.5 kg. My weight is reduced to 1 kg, but I can get the finish of the component. This is the component I required. After machining only, I can put this component for the real purpose, for the real application. See, 0.5%, sorry, 0.5 kg of material is reduced by means of the conventional subtractive manufacturing. It is a very simple. We are doing the shaving. Correct? Normally, the men are grooming their cheek by doing the shaving. Every day, they used to remove the hair. Correct? So that is before machining, after machining. If you want to make your face somewhat in a glittery finish, sir, I want to make some sort of glowing face in my body. So then I'm going for shaving. I'm removing the hair from the cheek. In such cases, what is that? You are grooming your cheek. When you are grooming your cheek, what is that? You are removing the material to get the good finish of your cheek. Similarly, subtractive manufacturing methodology is required. Whenever you are using additive, you need a subtractive manufacturing to get the finish of the component. That wastage is found to be very, very minimum compared to the other technology. That is a point I want to share it to you, my dear friends. That is something called buy. What you are buying is 1.5 kg. What you are flying is only 1 kg. So the buy to fly ratio is equal to 1.5 kg mass initial. It is reduced to 1 kg as a final product. 1.5 is to 1. That is that the ratio of the volume or the mass of the initial workpiece to that of the finished product. Sir, I'm going to play a beautiful video, sir. As I mentioned over here in the preamble, a single person is sufficient to do the modeling, import the design into the manufacturing area and additive manufacturing area where they are using that powder as a feedstock and laser as a heat sources for melting the powder to get the real shape of the component. See, a single person is the one, he imported the design of the impeller into that, and at a time he can develop 16 impellers. So he is imported and keep it on the EZ table, correct? Sir, wherever you are placing that component, that area alone is heated up. Once it is solidified, you are getting the shape of the impeller. So it is clearly mentioned, as I discussed in the previous thing. So component is built along the positive direction. Movement of the table is happened in the negative direction. So the power, according to the requirement, according to the size of the powder that you want to melt, you can select the laser power. It is maybe ranging from, even now we have something around from 1 watts to that 20 kilowatts. You have a variety of, because of the invention of the fiber lasers, you have a varieties of laser power. So from 1 watt, you can operate to 20 kilowatt. So the unmelt powder may be sucked out by means of an exhaust system. Like a normal vacuum pump, you can suck it and you can recycle once again this powder, because powders are so expensive. See, you can see it from this picture, from this video. It is an unfinished component. You need a peripheral machining. You need a subtractive manufacturing method to give the finish of the component. So that is why I have once again repeat the same word that I have put previously. You need a subtractive manufacturing methodology, even though you are working on additive manufacturing. You can remove, you can extract the component from the substrate. Once again, substrate may be used for rebuilding of the component. Varieties of material for varieties of application. Sir, sensor element, cobalt chromium, especially used for the dental crowns. This is for the medical application. So this is a beautiful machine. We have a DMG Mori. So this machine is having a technology of both Japan as well as the Chinese. Japan as well as the German. Japan, they have this Mori machine tool, and this DMG is belonging to German. So they have tied up, they have created this machine. Most of the aerospace industry, they equip this DMG Mori machine. In addition to that, they have a hybrid. So after printing, after making out this product, you have a milling tool. The laser torch will be reoriented and milling cutter will come and it will finish the component. That is something called the hybrid machining, hybrid technology. That is also that. So now I have this beauty of IRR additive manufacturing. So as I mentioned earlier, low and medium complexity part. This previous video that I have showcased for the high complexity part. In such cases, you can prefer a DMG Mori. That's something like a technology what we have in the powder-based technology. But here, when you go for a low and medium complexity parts, you have a laser. You have a tick torch or a Mech torch or a plasma torch. You can put a substrate above that. You can lay the number of field beads according to the size, according to the shape of the component. See how beautifully the layers has been made. See, the bonding strength plays a predominant role here. You can have a unique strength. You can achieve a strength more than that of the original material. For example, if I procure a inconal plate and it is built on the filler wire using this additive manufacturing, if we compare that normal plate with the build plate, your strength is very high because you are changing, you are metallurgically orienting the grains and the grain sizes are refined. Once the grain sizes are refined, you can achieve the adequate strength. A wall has been built. This is only for an example. Any shape you can build it. I am going to showcase so many things in the forthcoming slides. So when I compared these two, so it is highly cost effective. When you go for a wire arc additive manufacturing, highly cost effective. But the machine what I have showcased is something around 3 crore rupees. And powders are so costly. When you go for a normal filler wire, titanium 64, TI64 is only 15 kg, 15,000. But when you go for a powder, it is minimum, you have to get something around 25,000 rupees, 1 kg of powder. So when you go for a high complexity, prefer laser with the powder. Both are coming under the direct energy deposition, the so-called DED process. Both are coming under the category according to the requirement, according to the complexity of the part, you can select the process. So like a Lord Vinayaga, see the beauty of Lord Vinayaga, the thing is you are getting a different shape, different names for the Lord Vinayaga. Siddhi Vinayagar, something Valambudi, Edambudi, so many names are provided to the Lord Vinayaga. Similarly, for this wire arc additive manufacturing, you have endorsed with different names. You can see it is something called the shape welding. It is called shape melting, rapid prototyping, solid freeform fabrication, shape metal deposition, 3D welding. So varieties of name are provided to the same technology of wire arc additive manufacturing. VAM is better suited for low to medium complexity and medium to large scale parts, wing spars, panel of the stiffened panel for that entire pressure vessel, that you can do it with the help of this wire arc additive manufacturing. In addition, there is currently a demand for sustainable manufacturing. Everywhere, if you go there, when you go for a market, you can call it as an intelligent manufacturing and sustainable manufacturing. It is coming under the category of sustainable manufacturing and the green technology. It is not an hazardous process. If we have a smoke extractor, if we have a fume extractor, extract the smoke and deliver it to the atmosphere. So the area what you are doing the additive manufacturing, it is something under the category of green manufacturing technology. Environmental friendly process which have high geometric flexibility. Sir, VAM up to date, you can do a variety of things. As I mentioned over here, you can do a variety of process to understand the fundamentals of the VAM of the different materials. First, you can create a single wall, extract the sample, tensile sample, impact sample, fatigue samples, corrosion sample, wear sample, do an extensive study and report that extensive study. According to the report, the industry, the manufacturer will approach you, sir, I want this material, I want this VAM wall for this material, like that they will come and approach you. So to understand the fundamentals of VAM, the behavior of a single beam multi-layer open loop structure is widely studied, focusing on numerous aspects such as the forming appearance, design, residual stresses induced in the body. Because we are using welding, so you are heating the material, allow them to solidify. So heating and cooling cycles, this will lead to a induce of residual stresses into the substrate. You want to reduce the residual stresses to avoid the distortion of the substrate material. And welding process parameters variation, doing with the art of design of experiments or using the ANOVA analysis to find out the parametric effect on the weld bead geometry. So many things we can do it with the help of this VAM process. And as I mentioned here, this is the process flow, a beautiful process flow. It is applicable for all the manufacturing process, started with the CAD model, orient the CAD model according to the VAM, because you have to do the final finish of the component. For that, you have to give the cushion effect. If the thickness is 1 mm, you want to increase this to 1.2 mm. 0.2 material should be machined to get the finish of the component. Design adjustment of VAM, do the camp path tooling, that is of find out the G codes and the M codes, how to deposit the material and assign the process parameter, do a subsequent simulations to find out the effect of process parameter. As I mentioned earlier, the residual stresses, how the stresses are induced in the body, what about the temperature, it is reaching 2000 degree or less than that of 1500, like that you can do all the finite element simulation and do the VAM manufacturing. Then you can go for a shape and deformation control and then go for a CNC finishing of the component. Finally, you can use the coordinate measuring machines or a well-automized CMM machines to check the component, to get the dimensions of the finished component. This is how it has been carried out extensively, from starting from the scratch, from the model to the real product. Finished product can be endorsed, maybe checked or verified through the customized requirement or according to the requirement of the customer. In addition to that, you can create a three-dimensional digital model, machine it, and then go for a three-dimensional visual inspection, whether you can have an inherent flaw, you have a pose, or you have a porosity, like that. You can do that online inspections and you can finish the component and deliver the component to the customer. Sir, if you are using a defective filler wire, sir, the top one shows that defective filler wire, it is replicated, it shows on the end product having a high porosity. You see, the lot of black color marks are available in the micrograph that indicates that it is having a high porosity level. And we have a defect, if it is not ended with it is a flawless filler wire, sir, then you can report a very good quality product. So with the help of Rion et al, I have projected this information to this forum. And sir, not only on that original product, that you can also play with the human body. This biomedical implants and also this prosthetic components, nowadays they are working towards in printing this component through this additive manufacturing route of laser and also by means of this wire arc additive manufacturing. According to the requirement, according to the precision required, you can select the process. You can switch either with the powder or by means of that arc technology. Sir, these are all the some of the informations to give a comparative study between the conventional manufacturing methodology and with respect to that wire arc additive manufacturing. You see, buy-to-fly ratio that is mentioned in the red color font. Conventional machining is of 11:5. Sir, this entire 10.5 kg is added to the product cost. What is it? 11.5:1. Very high buy-to-fly ratio. What it means that from a 250 kg billet, it is reduced to 21 kg of a finished part. Sir, if I want to get a 21 kg of the finished, you have to put a 250 kg when you go for a conventional machining route. But when you go for a VAM, when we are adapting the VAM technology, you see 21 kg, sir, 24 kg near net shape, 1.14:1, deposited part of 21 kg, 24 hours for the builder. For the entire day they have spent for building out that material, out of which 30% they are keeping it for cooling that material, because subsequent process, one above the other, you have to put the material. For subsequent process, you have to keep a dwell time to allow them to solidify. If you are doing it subsequently without doing that dwell time, then you are not getting a very good strength as per the requirement. And you see, another beauty, you can play with that. See, small spots are required. Very small spot welding are sufficient to create a structure, a human structure. It's sufficient. A skeleton of a human being. See, head has been made. Now hands are developed. See, by single spot, one above the other, you can get the beauty of that structure. Within 1 or 2 minutes, you can complete this structure. That is the beauty because of the high deposition rate of the wire arc additive manufacturing process. Clear? This is one of the applications, what I mean here. And sir, this is a very beauty, friends. So please open your eyes, my dear friends. Very, very important. See, it is also used for repairing of materials. A very, very important technique. This is the only technique available in the world where you can go for a repairing. For example, I have 3 wings in my fan. There is a problem in one wing because there is some sort of cracks and it has been damaged. You have to remove it. Instead of replacing the entire fan, you remove that the worn out part, you remove the worn out part and remove it by means of any conventional method, by means of AXA or something like that, and lay a robo very close to the structure, get the shape of the wing, deposit the filler wire according to the shape of the thing. So that is clearly depicted in this picture. You see, first 2, 1, 2, totally 3 wings are there. First 2 wings are something like a beautiful wings. There is no part, there is no damage to that wing. But another 3rd wing, it has been replaced by means of a VAM. So you can go the repairing of the component. For example, I have a gear of size around 250 mm diameter. I have made a wrong hole at the center. Instead of 10 mm, I have made it as a 12 mm. Then 2 mm, I have made it wrongly. So what we can do, you can put a robo very close to that. What about the material? According to the material, you can select the filler wire, deposit the filler wire for 2 mm, go for a final machining to get the finish of the component. You can reuse the gear once again instead of replacing the entire gear. That is the beauty of the process. What about the comparison? With the conventional, you have a saving of 69%. You have a saving of 55%. It is not merely taken out from the literature. It is a real data where a machinist has been deployed for calculating all this information. And as I mentioned earlier, varieties of material you can build it. And also you can also work with the refractory materials. The refractory material, the melting point is around 3000 degrees centigrade. That is possible because the arc energy we are developing is something around 10,000 degree Fahrenheit. Even you can achieve 20,000 degree Fahrenheit. So you can melt these refractory material very easily. Compared with the other processes, we are crossing that average level. We are crossing beyond 5 levels rating in all the cases, something on build rate, complexity, accuracy, cost savings, material utilization, mechanical properties. You see very close, 9 rating out of 10, we are achieving around 9. Post-processing equipment, platform flexibility, plot size. We are crossing beyond that 5 rating level, and there is a different methods are available. So deposition strategy, where you have to deposit from left to right or right to left, from top to bottom or bottom to top, like that. Based on the deposition strategy, you can achieve the microstructure. Once you achieve the different microstructure, it is directly leading to a strength of the material. It is directly correlated. It is directly equivalent to the material property that you could achieve with different deposition strategy. And as I climbed, once again, I'm making out the claim that this is the only process available in the world where you can orient the torch in different direction. See, the direction. You can horizontally, you can build the material. Vertically, you can build the material. Even you can do some sort of research for building the material on the overhead position. That is a touch because of the solidifications, because of the welding technology. You can lay the material, you can deposit the weld beads from left to right, right to left, from bottom to top or top to bottom. Normally, when we are climbing as a welding engineer, they will orient the touch with respect to the position 2G, 3G, 3G position. Even you can go for a 6G position. That is possible with respect to that van. And coming to the number of case studies, sir, what we are doing here, sir, without case study, how I can respect my technology? Sir, here, this is one in Rotterdam, especially in Netherlands, they have deposited this nickel, aluminum, bronze alloy, something around 298 layers. They can use it for the crane hook. See, when we are teaching the CAD, the imp, that is the crane hook, is the one of the difficult part to create in the SolidWorks or with the Autodesk Inventor, etc. Because all the cross sections are different from one another, correct? So where you can easily do it by means of this VAM technology. It is a proven. The entire weight of this crane hook is something around 400. I have provided the link informations. If you want, you can grasp more information, especially used in the marine application. What is the problem in the marine applications? Where we have a seawater, a salty water, you can have a corrosion, chloride attack will be there. So to avoid that, they are using a nickel, aluminum, bronze material to avoid the corrosion. Further, it will end up with the erosion. And this bicycle frame, this entire bicycle frame is created using this technology of this van. And the Dutch startup, it is called the MX 3D. Especially for startup people, this technology plays a predominant role. And what we are standing here, because without giving something like taking a literature, sharing this information to all is nothing helpful. Sir, we have experienced people here. We experienced ourselves by playing with this robo. I want to thank ODC Dagan for providing this welding robo, 6-axis robo to NIT Trichy. And we are playing with different varieties of material. I think there is some small issue in that video. Sir, this is something about a Inconel 65, 625 before machining, after machining. You can get a finish of the component. After that, they are going for a dimension technique, something like that to check the dimensions to find out the accuracy of the model. And there is another material where you can go for a combination of material. One video is playing automatically. Half machined, bottom is kept as is to find out how peripheral machining is required to get the finish of the component. And it is not only for aluminum, you can go for a filler wire of titanium, you can go for a carbon steel, you can go for a combination of material of copper laid over steel. That is also possible. That is also possible. We tried, we obtained the results, and the article has been published in the open forum. You can check during your free time. And also we are working with the nuclear material. It is something like a niobium thing. It is something like a 347 SS. We have created a wall. We have machined it to find out the buy-to-fly ratio. From that, we have extracted the sample for finding out the strength of the material. And this with the help of the Cranfield University, because I took that information from the literature of Cranfield, where they are going for post-processing. After completion of each layer, they are rolling. They are putting the rollers to roll the material to induce the strength of the material. That also they are doing with that to get the finish of the component. This is one of the literature that I took from the open literature. Something like a refractory materials. They have heated more than that of 3000 degree and they have deposited the material. Something like a high quality tantalum components, that also possible by means of additive manufacturing. So my part as I'm a finite element simulation man, it is very important to find out what about the stresses induced in the body. So this is the base literature where we have gathered that information. With the help of this literatures, we have simulated. I want to thank my scholar, Dr. Arun Kumar. He only made a beautiful analysis, and the bottom one, you can see that the effect of residual stresses on the component. You see there is a big distortion of the material. Once you are laying the material, because of the residual stresses, the entire material is distorted. So this will give the awareness that for checking the process parameter and also the deposition strategy. You can predict the temperature distributions, you can find out the residual stresses and followed by the distortions by doing the finite element simulation for changing the process parameter. That is possible only with the virtual platform or by means of the numerical simulation packages. Okay. So without these references, because we are approaching very close to 9:30, so it is something around 9:21. I'll open to the audience for another 4 or 5 minutes because we are going to bed at around 10 o'clock after taking your Kana. Now the session is open to audience. Before that, I want to thank all these references because these are all the references made me to prepare this presentation, and I've shared this information. They are the knowledge that we gained, the experience that we gained at AIT Trichy, and also during the literature. I have shared this information. I also thank my friend Prabhahar for giving me an opportunity to be a part of this wonderful ATAL program. Thank you.
Thank you, sir. It was a most informative and very elaborative presentation. The way you presented showed your expertise on this domain. With this note, I open the session for questions. We will take it in the positive way that you explained everything, whatever required.
Otherwise, you can just open the chat box. I just open my chat box. If time permits, you can share the thing. I'll just open it for another 2 minutes. If you want type anything in the chat box, I readily answer to the queries posted in the chat box. Please.
Yes, sir. Yes, sir.
So if there is no more queries, you can put the feedback, something like that. No, sir, it is totally waste or totally good. Anything, you just open it and put something in the chat box. I am very interested to see what is there in the chat box.
So they're giving the feedback, sir. Wonderful and informative session. Thank you, sir. Nice session, sir. More informative.
But I am not seeing anything in the chat box. Okay. I didn't scroll it down. Okay.
Yes, sir. Yes, sir. It's beneath.
Okay. Very good. They have posted the question. Extremely sorry, friends. Oh, Prabhahar, yes, you have asked me what is the question, size of the specimen, sir. Very beautiful question, because I expected this question after making out this presentation. See the filler size. When you go for a VAM, wire or additive manufacturing, the minimum filler size, the diameter of the filler wire readily available in that market is only of 1.2 mm diameter. But when you go for a powder technology, you can play with the powders size of around nano or in terms of micrometer level. But when you go for this VAM, it is only of starting with 1.2. That is why we are claiming that those who are working on VAM, they are claiming that it is only for low and medium complexity. A minimum size component is very difficult to printable using this VAM technology. Then they can go for that. They can shift their perception. They can shift their idea towards that powder-based technology. Based on the component, you have to select the process. What is residual stress is a significant issue. Yes, it is very important thing, because you are melting the material. Once you are melting the material, and upon solidification, you are metallurgically affecting the material. Automatically, stresses are induced in the body because you are constraining. You are not allowing the material to move freely, to expand it freely. If you are constraining any material, stresses will be induced in the body. See, now the workshop has been organized at around 7:30 to 9 o'clock or 9:30. Automatically residual stresses are induced in your body, because we are not allowing to go for taking a food. If I am having an interactive session, I can call each and every one and I'll raise the question. We are not allowing you to move freely. Automatically stresses will be induced in that body. In order to relieve the stresses, you have to move freely. You have to expand the material freely. That is the main information. And amazing. Oh, that's all. Any other question? Okay.
Yes, actually,
for giving a good feedback.
For adopting the 3D printing methodology for the current manufacturing scenario for advanced manufacturing technology, as compared with the conventional manufacturing process, several pain points are there, like initial setup cost and scalability aspect and production time. All those things are little considered as a pain points for in that manufacturing sector. How to overcome these issues? Whether you have to adopt in that scenario, or else is there that what is that advantage side? We have a very good appreciation in this 3D printing.
No, thing is, as I mentioned earlier, you have a freedom of design. That is a unique feature of additive manufacturing. You can design your own component. But for all the process, if you do a simulation or if you do an experimental thing, you need pre-processing and also you need post-processing. Similarly, here, how to convert your design to a original model, you have to do a pre-processing. For that, time is inevitable. You have to consume some sort of time, but the time is something a useful one to convert the component. Once the component is developed, this code will never ever change. You can keep it as an inventory, you can keep it as a treasury in your gold box. Anytime you can retrieve it and you can go for rescheduling the thing. You can go for relayering the component. N number of times you can do it. For starting the first component, you have to do the pre-processing. You know how to convert your design to a product through powder technology route or through welding route. That is very, very important.
Okay.
But once it's done in a superb way, you can get a beautiful product. You can get a strengthable product. It will never ever fail under different conditions. That is the beauty of this process. Okay, thank you. Thank you. I think no more information, no more queries in the box. I will share the presentations. Normally it is not a big thing. I'll share it because nothing is confidential here. Because what are the experience that we gained at NIT, I just share that information. Surely I'll share my presentation to the audience.
Thank you, sir. Thanks for your wonderful presentation and also the thought-provoking information regarding the 3D printers and the machineries available, facilities available, and the techniques available in the current scenario for the product formation.
Thank you. Bye. Good night. Have a sweet dreams.
Thank you.
Sir. Thank you, sir. I request Mr. Kalyan Kumar to post the feedback in the group. Kindly fill the feedback form. The feedback form is valid for 45 minutes. I request everyone to fill the feedback form for the second session also. For every session, there will be a feedback form. Please fill the feedback form. With this, the day one session gets completed. We will all meet you tomorrow with the wonderful session. Thank you. Thanks for joining for today. Have a pleasant sleep. Thank you.
Before closing, stop the recording, Sindhil.
Sure.